Improved Variable Modification Handling in Mascot 2.7, presented by Patrick Emery from Matrix Science Limited. Modifications are an important topic in database searching. The main focus of a study may be to characterize post-translational modifications with biological significance, for example, studying phosphorylation patterns. In other cases, the modification may not be of interest in itself, but may be required to get a match during the database search. Oxidation during sample preparation is a common example of this. Some modifications are the result of deliberate derivatization as part of the experiment, for example, using isotopic labels for quantitation. During the database search, modifications can be handled in two ways. Fixed modifications are where every instance of the target residue are modified. These are simple to handle because it is effectively just a change in the mass of the residue. The more complex case are variable modifications, where just a limited number of the residues are modified. In this presentation, we'll be looking at some very important changes in how Mascot permutates the possible arrangements for variable modifications during a database search. When we released Mascot 2.7 in January this year, tucked away under other new features was this: improved limits on variable modifications, better site localization by introducing separate caps on the number of distinct modifications in a PSM, the number of modified sites in a PSM, and the total number of arrangements to be tested. So what exactly do we mean by this, and why is this a significant improvement to the way Mascot can handle variable modifications? First, let's define what it is the software is having to do when looking for modified sites. Let's consider this slightly unusual peptide comprised of 8 lysine, 4 serine, and 2 threonine residues as an example. If we carried out a search with lysine acetylation and phosphoserine and threonine, if the precursor mass and tolerance allowed for a single lysine acetylation, there are just 8 possible arrangements of this. Likewise, if a single phosphorylation was possible, there are just 6 possible arrangements. However, the number of possible arrangements increases rapidly as we consider more modifications and modifiable sites. If we need 2 lysine residues to be acetylated to match the precursor, we now have 28 possible arrangements. Add in a single phosphorylation, and we now have the possible 28 acetylation sites, combined with 6 possible phosphorylation sites, for a grand total of 168 possible arrangements. This is the so-called combinatorial explosion, and it's one reason why some searches with a large number of frequent modifications can take a long time. Here's how variable modification permutation works in Mascot 2.6 or earlier. There is no upper limit on the number of modified sites per peptide. However, permutation of the modifications options does have built-in limits. If the maximum number of arrangements for a peptide is less than 16, then all possible permutations are tested for matching by Mascot. However, if there are more than 16 arrangements, then a second approach is automatically used, where a sliding window is applied to the peptide. This is to prevent the search from getting too slow and taking too long. In general, the approach works well. However, it isn't without its limitations. If a peptide has less than 16 variable modification permutations, then there are no issues, as all possibilities are tested. It's in the cases where the peptide has more than 16 possible permutations that issues can arise. The sliding window method tends to cluster modifications on adjacent modifiable sites, and it will often stop before 16 different permutations have been tested. In Mascot 2.7, we've taken a different approach. We use a single, consistent permutation method. There's no switching between different methods. The new permutation iterator samples arrangements using a uniformly random scheme. The operation of this is controlled by 3 user-definable settings. Max pep num var mods. This specifies the maximum number of different variable modifications which can be applied to a peptide. Max pep num modified sites. This specifies the maximum number of residues which can be modified on a peptide. And max pep mod arrangements. This specifies the maximum number of arrangements of an individual var-mod composition to test. Mascot 2.7 ships with the following default values for these parameters: max pep num var mods 3, max pep num modified sites 5, and max pep mod arrangements 64. These have been chosen to give a similar speed and depth of search to Mascot 2.6 or earlier. So for most searches with variable modifications, you won't see major differences in the results if you repeat an old search on Mascot 2.7, assuming you're using the same database release, of course. There are two main cases where you might want to change these defaults. Decreasing any of these values will reduce the search space, as fewer arrangements will be tested. This will decrease the search time, so if you are looking at a sample which is not highly modified, and where definitive site analysis is not the aim of the study, you may wish to decrease some of these values. However, if site localization is important, or if you're looking at a highly modified protein such as histone, then you may need to increase these limits in order to gain accurate modification localization results. We'll take a look at examples of each of these cases later in the presentation. If you need to change these settings, then you can set the values globally via the configuration options under Mascot Configuration on your Mascot server. However, it can be difficult to set limits which are good for all experiments. If you have a middle or top-down experiment alongside a standard bottom-up experiment, you may well need very different settings for searching data from each experiment. In those cases, you can specify the parameters locally by embedding them at the head of the MGF peak lists file. The embedded parameters will override the defaults specified by your Mascot configuration. If you're using Mascot Daemon and using a data import filter like Mascot Distiller to process raw files into peak lists, then you can add additional options like these to the .par parameter files. Just add them at the end like I've done in this example. This will allow you to add the parameters when you don't have immediate access to the peak lists which will be submitted, or if you're searching peak lists in a format other than MGF. One of the consequences of these changes are that we can speed up error-tolerant searches. To test this, I've taken a subset of a mouse label-free dataset available from the PRIDE public repository and produced a peak list of approximately 20,000 MSMS spectra. The samples are lightly modified. The information in PRIDE specified oxidation and deamidation as variable modifications and carbamidomethylation as a fixed modification. I've then searched the peak lists using Mascot 2.6 and Mascot 2.7 using the default permutation parameters. When Mascot 2.7 carries out an error-tolerant search, the max pep num modified sites and max pep mod arrangement settings are applied directly to the error-tolerant pass. The max pep num var mods setting applies only to the first pass search, so we allow for one additional error-tolerant modification to be applied in the second pass search. The search had a total of 4,437 PSMs above the homology threshold, including 629 error-tolerant matches, and took 95 minutes with Mascot 2.6. With Mascot 2.7, you can see we have a very slight increase in the number of significant and error-tolerant matches, but the results are essentially the same. However, the search was significantly faster, taking 79 minutes. That's 17% faster. One of the main reasons for this is the limit on the number of modified sites applied by the max pep num modified sites setting. In Mascot 2.6, there was no limit, so, especially on longer peptides, the error-tolerant search pass can end up testing a lot of combinations and modifications which don't actually yield reliable results and are therefore never reported. The max pep num modified site setting of 5 in Mascot 2.7 is preventing this, so the search takes less time. This particular sample is not very heavily modified, so I should be able to get the same or very similar error-tolerant search results using narrower permutation settings. Doing this should also reduce the search time. To test this, I've repeated and timed the search on Mascot 2.7 using a range of different permutation settings. Where a parameter isn't specified, the default value is used. Once the searches have completed, you can see the modifications which have been identified and the number of PSMs containing the modification by expanding the modification statistics for all protein families section on the protein family report. As you can see, the list of the top most identified error-tolerant variable modifications identified by the default and search for permutation settings are almost identical. We actually get one extra match from the lower permutation settings. This is probably due to a marginal match becoming significant due to the reduced search space. We get very similar results from all the searches on both the standard first pass search and the error tolerant pass. Reducing the maximum number of modification arrangements tested to 32 gives us a 14% improvement in the search speed, while reducing the number of modified sites allowed to 3 gives us a 21% improvement. In both cases, this is because we're reducing the search space, which has quite a big impact on the time taken for the error tolerant search. Reducing the maximum number of different variable modifications per peptide doesn't improve the search speed. In this case, that is expected because we've only got 2 variable modifications selected in the search settings, so changing this won't have any effect on the search space. Lowering all 3 settings gives us the fastest search, which is now 28% faster than using the default settings. This is mainly due to the combination of the reduced number of mod arrangements and modified sites. So when you're searching datasets which are not highly modified with Mascot 2.7, you may wish to consider lowering the permutation settings to speed up searching, especially if you're doing an error-tolerant pass. Our second example combines the 2 reasons you might want to increase the variable modification permutation limits. I took a single raw file from a human histone H4 middle down dataset available on the PRIDE repository. The authors had digested the sample with ASP-N and selected the first 23 residue peptide. Being a histone protein, this peptide is highly modified, and the authors were looking for changes in modification patterns across the cell cycle. The variable modifications for the search were taken from the paper. As you can see, this peptide contains a large number of possible modification sites, particularly for acetylation and methylation. Because of this, it's clear that the default permutation settings won't be sufficient to give us accurate modification analysis. I processed the raw file in Mascot Distiller and exported an MGF file with the fragment ion masses decharged to 1+, then searched using Mascot 2.6 and Mascot 2.7. For the Mascot 2.7 searches, I changed the permutation settings. I set max pep num modified sites to 11 and max pep num var mods to 7, so that all possible residues could be modified and allowing for all variable modifications. I then searched using a range of values for max pep mod arrangements from 64 up to 512. With Mascot 2.6, we identified 81 distinct proteoforms, that is, distinct modification patterns. As you can see, using Mascot 2.7 to do a deeper search into the variable modifications, we have identified significantly more possible proteoforms, although there was no need to go above 128 arrangements in this case. We hit a maximum number of proteoforms of 109, and increasing beyond 128 arrangements will have done nothing other than slow the searches down. Let's take a look at a few examples of the differences between the results for Mascot 2.6 and 2.7. In all cases, the Mascot 2.7 results have been taken from the search where we used 128 modification arrangements. Here we have a very good match from Mascot 2.6 with an iron score of 112. It looks reliable, however, there is a problem. Arginines 17 and 19 are not methylated in vivo, and indeed, if we look at that region of the sequence ladder, we have no matching fragment ions in that region. What appears to have happened is that we've got the clustering of modifications that I mentioned was an issue with the sliding window method used in Mascot 2.6 for peptides with a lot of variable modification permutations. I think we'd have to conclude that while we have the correct peptide sequence here, the modification pattern reported is incorrect. Here we have the best match to the same peak list in Mascot 2.7, and we have an even better match. The iron score is now increased to 158, and the modification pattern is much more believable. If we look at the sequence ladder, the region around arginine 17 and 19 is now covered. Here we have an example where Mascot 2.6 failed to find any match for the peak list. But with Mascot 2.7, we've got a good match to the same peak list. Presumably the correct modification pattern was not tested by Mascot 2.6, preventing us from getting a match. So to summarize, permutation of variable modification arrangements has changed significantly in Mascot 2.7. This has been done to address some shortcomings in how earlier versions of Mascot handled this for peptides with large numbers of possible modification arrangements. The new variable modification iterator is controlled by 3 parameters, which can be set globally and overridden locally. This gives you a large amount of control over the depth of search when Mascot assigns variable modifications. By controlling these parameters, you can either reduce the depth of the search. This will speed up searches of lightly modified samples without affecting your results. Or you can increase the depth of the search, which is important if you're interested in site localization or in studying highly modified peptides.